I'm Kevin Zhu, and today I'll be talking to you about neuromorphic swarms taking milling from sim to real using spiking neural networks. So I will hold you all in no suspense. This is the result of the work that I'll present today. This is what we call a mill of robots. In this work, we have tried to answer the question, can we use spiking neural networks, or SNNs for short, to mill on a swarm of ground robots? Now, you might think that they're just going in a circle. It looks kind of easy. So the first part of my presentation, I'm going to try and convince you that this is actually difficult. Then I'll present a process we designed to make it a little bit less difficult to replicate this behavior on a wide range of robots. Next, I'll explain our motivations for why one might want to have neuromorphic concepts in a swarm in the first place. And finally, I'll present our case study of how we sort of discovered how to recreate this behavior on a new robotic platform and discuss some of the challenges we experienced. So a big part of why this is difficult is the constraints. Our primary interests are in emergent behaviors. We want these robots, these agents, to create this mill, but none of these robots should actually have this as a personal goal. None of these agents should really want to make a circle shape. This is best illustrated by a similar natural phenomenon, the ant mill. These ants have trapped themselves in a never-ending cycle of following the pheromones left by the ants in front of it, which in this case leads to a never-ending circle of death. I think the separation between local agent level rule and global behavior is very clear here because no ant should want to form a death mill, but given the agent control law and certain initial conditions, this detrimental swarm level behavior forms. Now, roboticists should probably like their robots to be used for less morbid behaviors. At the bottom of the screen, we see that some robots are pushing red cans together. This is a swarm-based solution that humans have engineered to the problem of clustering objects. But that separation between local agent level rule and swarm behavior makes designing these behaviors difficult. In the middle, we can see an emergent amoeba formation in simulation. This was created by a student painstakingly tweaking parameters until they got something interesting. This is why milling can be so difficult to recreate. It's because emergence can be difficult to understand and requires a lot of intuition or a lot of experimentation. For me to explain why emergence is something we care about in the first place is a little bit more difficult, so I'll ask you to hold on to that question. And for now, I'll just say that we see a lot of emergence in nature, particularly with swarms of very small and not particularly intelligent creatures. Instead, I'll now explain the actual rule behind milling. To replicate milling in the lab, it was found that something as complex as pheromone sensing was not necessary. In fact, it only requires a binary presence sensor. You either detect if there is or isn't another robot in this region in front of you. We call the sensed region the agent's FOV, or the robot's field of view. It has a limited range and is a limited angular region in front of a robot. This sensor model is not only simple to conceptualize, but plausible to implement using a wide variety of technologies such as cameras, IR transmitters, rangefinders, GPS, or even UWB sensors. There are just so many different ways you can make this sensor. And the controller that was found to produce milling is equally simple. If you see something, move forwards while turning left, and otherwise move forwards while turning right. This is a binary sensor hooked up directly to binary actuation outputs. However, there's a bit more nuance to it. The forward speed and the speed at which the agent turns is actually important. In the controller, you'll set it to move with a particular forward speed, and when you turn left or right, you do it with a certain angular velocity or turning rate. And we found that for a particular robot, you actually get different behaviors with different combinations of these. So, we ran some real-world experiments to spot check certain combinations of this forward speed and turning rate. And here's what we found. On one end of the spectrum, if you have the parameters up in this corner, you get the robots dispersing all over the room. But in this corner over here, the robots sort of end up clumping together. And in the middle, you get this nice large region where the robots mill in a stable formation. And here are the simulations, and here are the real-world experiments to match. So this also depends on not only the initial conditions where we set up the agents, but also on the other robot parameters. How big is the robot? How well do they sense? What is the field of view and the angle that they sense at, the maximum speed, but also other things like how noisy is the actuation and how much variance in all of these parameters is there among the population at large. That's a lot of stuff to keep in mind while running experiments. I should note now that each of these stars or symbols on this chart was an individual experiment that we ran, a real-world swarm deployment. But those were only the ones that actually yielded relevant data. I'm not showing you all of the times I had a robot with a wheel fall off, or a sensor broke, or one fell over, or the batteries weren't charged. Setting up experiments and collecting this data manually is time and labor intensive and error prone. And while automation can help speed things up a little, things like motion capture systems tend to be really expensive. And at the end of the day, a human still needs to be on hand to fix things when they go wrong. Sorry for all of that. Can you tell these robots were quite fun to work with? So this is part of the work we did previously, in which we grappled with the question of how do we find the right combinations of parameters to actually get milling on a robot with this binary controller. But actually, we can generalize this a little bit. For a binary sensing robot, let's think of the controller as a black box which outputs desired velocities for any moment in time. What controller should we use to get a certain desired behavior? And how do we do all of this without losing our sanity? So this is what we did in a previous work. We came up with this process for how to use simulations to speed things up and reduce the number of real-world robot deployments on the road to getting a particular behavior. Using simulations allows us to test thousands of possible controllers in the time it would take to run one or two experiments on the physical robot swarm. But now we have a new problem. We're not testing these controllers on the real swarms anymore, so there's probably a gap between how the idealized simulated robot acts versus the real thing, which has imperfections in how it senses and how it moves. And keep in mind, every robot might be slightly different, so it's not just a problem of making a single simulated agent match a single real robot. You have to consider, at minimum, a sample of agents. We suggested that previous works either overly relied on high-fidelity simulators to create these emergent behaviors on real robots, or used very capable robots with reliable sensors, well-calibrated actuators with repeatable precision or closed-loop control, and in some cases, compute-intensive perception or planning algorithms. But more reliable agents are expensive, diminishing the value proposition of using large numbers of agents in swarms anyways. So our process is this. First, we will create a model for the sensing and actuation characteristics of the agents. Here we suggest measuring, or incorporating or at least measuring the idiosyncrasies amongst the swarm, so you have an understanding of how one robot might be different from another. Then we take this model and we program it into a basic simulator. In the previous work, we just used the simulator to execute a simple grid search of the parameters to the binary controller, but we suggested that you could do this with something like an SNN perhaps, a little bit of foreshadowing. But anyways, once you find something in the simulator, you can test that on a real-world swarm deployment, and based on that, you'd have data to make judgments on whether you need to upgrade your sensing or actuation capabilities or your simulator, or if you just need them to match better somehow. And the results were what you just saw. We ran a few deployments in the sim, and we matched them to real life, and we got milling. So I hope I've explained now why milling is, in a certain sense, difficult to achieve using emergence. And I think you may have gotten a glimpse of why we want emergence in the first place. It enables interesting swarm-level behaviors from robots or agents that are cheap and dumb, and not much more capable than insects. And I've shown an overview of the process we developed for how to use simulations to reduce the number of real-world swarm deployments in order to find those local agent-to-agent interaction rules that result in a particular behavior. Next, I'm going to briefly talk about why we want neuromorphic concepts involved in this, specifically spiking neural networks. Now, originally, I'd gotten it into my head that spiking neural networks, or SNNs, would probably be good for operating on streams of information, data that's fed in over a period of time. That's exactly how a lot of RL, agent-based robotics learning problems are formulated. Where a traditional MLP network only operates on a single vector of information, SNNs natively operate on sequences of information, retaining some degree of memory. So this is why we thought SNNs might be particularly applicable to robotics. But how can I ignore, of course, the usual rhetoric with SNNs, size, weight, and power? These concepts fit very well with all the things I've discussed previously. Large numbers of cheap robots with tiny footprints, like an ant. One might imagine a relatively large SNN running on something like the Harvard RoboBee, and being produced using application-specific analog ICs in the far future for pennies on the dollar. But for now, let's just see if SNNs can even be used for swarm robotics at all. Our old robotic platform shown previously was no longer available to use, so to answer the question of viability of SNNs for swarms, we chose here an off-the-shelf educational robot to use as our test platform, the HiWonder TurboPi. The platform is a small ground vehicle about 20 centimeters long. It has 4 independently driven Mecanum wheels. However, we've restricted its moveset to only move with unicycle dynamics. That is, it can either only go forwards or backwards and turn left or right at a given speed and angular velocity. The onboard sensing package consists of a webcam. We don't use any of the other sensors that it has, and that includes there are no wheel encoders. In this slide, you can see the only two hardware modifications we made, consisting of a little plastic stand just to hold up this ping pong ball a little bit taller, and some skirts which prevent the robots from climbing over each other in cases of collisions. In every other respect, these robots are exactly as they come from the factory, except for software. So for this new robotic platform, we put it through the same process as we described previously. First, we characterize it, then we use the resulting model in a simulator to find an SNN that gives us our desired milling behavior in the simulator, and then we attempt to replicate the simulated experiment on the real robot, and then go back and fix anything that breaks. Despite the availability of a motion capture system, we wanted to show that this characterization process doesn't require an expensive mocap suite. So we manually timed and measured the movements of robots in order to map the robot speed commands, which range from 0 to 100, to an actual meters per second value over here. We did this for a variety of combinations of speed and turning rate. Each of the colored dots you see on the left here is a single measurement of either the actual recorded velocity or the actual measured angular velocity for a particular robot, and for a particular combination of speed and turning rate. Again, while the Mecanum wheels can be used to create omnidirectional movement, we don't allow them to side strafe. We also note that the robots don't have wheel encoders, so this actuation is open loop. We characterize the field of view region for the camera sensor by measuring where a simple OpenCV color contour algorithm is able to detect those green balls. We average those FOV angles and ranges across a wide variety of robots from our fleet. We then implemented this robot model in our simulator. We're using a simple top-down 2D simulator originally written by Connor Matson at University of Utah using Python and Pygame. This simulator operates on discrete time steps during which each agent updates its sensor and then outputs some desired velocity and turning rate. Now I will talk about how we achieved milling in simulation first, and because we're using the characterized TurboPy in our simulation, there should be a hope that if we can learn milling in the simulation, we can then send the learn network to the real robots, the TurboPys, and get those to mill. I'll talk about exactly how we use those measurements when I talk about how we hook up the network to the sensors and actuators, the action space and encoder and decoder setup. But first, I'll talk about the objective function we use and the evolutionary strategy that uses it. So this is our objective function, which we call circliness. It is a relatively simple to understand metric at a higher level because it ranges from 0, which is not a circle, to 1, the highest possible value, which is supposedly the ideal circle. To calculate circliness, we first calculate the average position of the agents, which we take to be the center of the swarm. Then we measure the furthest and closest agents to that point. If this delta is small, the agents are closer to a circular formation. We also incorporate a notion of tangentness, that is, they all face tangent to the circle, as opposed to inwards or outwards. We also average this metric over a time window because we want the robots to form the circle not for a brief moment in time when we take one measurement, but over a period so that they maintain this circular formation. And we'll take this measurement subject to the same initial starting condition, the same environment. All of the agents in the simulation will be roughly the same, taken from an average of those measurements from earlier, and we'll use the same controller. We'll give the same controller to every single agent, but we'll give them independent memory, and we'll run the simulation for a fixed number of ticks, and then we get a circliness value associated with it. So that is for each network, we get an associated, we'll run the simulation and get an associated circliness score. We then start with a randomly generated population of networks. We're using eons for this, which involves not only the thresholds and weights and leak parameters on each neuron and synapse in a network, but also the topology or the structure. We run simulations in parallel to determine a circliness for each network, and then we use tournament selection to decide which networks survive, and we mutate the population while also adding some newly generated networks in the mix. The SNN simulator we're using for this is Caspian, which was developed at Oak Ridge National Lab. It uses a leaky integrated fire neuron model, which incorporates leak, axon weight, and axonal delay. It operates in discrete time, so all events happen on a fixed clock. For any given processor tick, there either is or isn't a spike coming from a neuron. It was originally developed to have an FPGA implementation, so there are some hard limits imposed, such as a maximum synaptic delay of 255 steps, even on the C-based software simulator we're using. To be clear, we have the swarm simulator, and each robot in the swarm has an instance of this C-based Caspian simulator on it to simulate the SNN. So we've got a bunch of simulators inside that outer simulator. And on each step of that outer simulator, each robot will take its sensor reading. We use a binary to one hot encoding, so we send a constant train of spikes. If we see something, we send a constant train of spikes to one of the input neurons, and if we don't, we send it to the other. This is then used to propagate spikes through the network, and then they hopefully end up at the output here. Our rate decoding setup is also periodic, but we account for the propagation time by running the processor for a few extra steps just so that there's enough time for a change in the sensor readouts to be reflected in the portion of the output raster that matters for this particular tick of the outer simulation. And if we let the evolutionary system run, the networks hopefully evolve to optimize circliness. Here we show a nice output of what this looks like for the previous work that we have, where we run the robots, where we run the older platform. However, this is still the same population size of 100 over 100 generations. Sometimes it does take longer than 100 generations, and sometimes shorter. It depends a lot on the encoder and decoder setup, but also there's a lot of stochasticity in the training. And here is a live simulation along with a live visualization of the network. On the right side is a network for a single robot. At the top, we can see two input neurons, one for if something is sensed and one for if it doesn't sense anything. And we guarantee that one of those two neurons is always getting spikes. At the bottom here are our output neurons. We have two pairs of neurons. One is for a pair of requested velocity, and the other is for the requested turning rate. We use rate decoding, or more simply stated, we count the number of spikes from each neuron within a periodic cycle, and we take the difference in number of spikes from the neurons in the pair, which allows for negative values, and we can think of this as gas and brake on neurons on the left, and turn left or turn right for the other pair. And just to be clear, this is a human-specified encoding and decoding setup, so the action space here is defined and not learned. What is learned is how to connect the input, the sensor data, to the control output. Here's also where the sim-to-real connection comes in. We give each robot the same FOV and sensing range as those we measured, and we also performed a linear mapping of the number of spikes received to the speed and turning rate based on the measurements we took earlier. So those two slides were for an older robot that we have. I haven't been able to generate those fancy side-by-sides for the new robotic platform, but that's why we have 6 robots here. We found that neither the SNN or the binary controllers had much luck for this new platform beyond 6 robots. 7 robots, even with our most finely tuned binary controller, tended to grow the circle beyond the sensing range and then collapse. So I should also note that the evolutionary process is quite stochastic. There is some randomness in there, but the end result for high circliness scores above 0.9 tended to look very similar. So everything I'm about to show you is with a circliness score of above 0.9. And in the simulation, they all eventually look somewhat like this. Sometimes the circle will go clockwise and sometimes it goes counterclockwise. The circliness score doesn't really account for that, nor does it account for the speed of the agents or the size of the circle. And now I will show you what hopefully this near perfect Millen simulation looks like on the real robots, the TurboPis. So here we can see them hopefully forming the circle. Oh no, that's not a very good circle. And so let's try another network, and well, that's a little bit better, but it's not quite the perfect circle that we saw in the simulation. So we do have a theory for why this is. On the previous one, you can see that some of the wheels on the robots are not turning, even though when we checked the output of the network, we actually saw that these wheels were supposed to be turning. So this shows us that there is some kind of sim-to-real gap going on here. And our hypothesis for why this is that there is some amount of static friction within the gearbox, because if we manually test transitioning from 0 wheel speed to some very low wheel speed, then the wheels don't turn. But if we go from a higher speed to a lower speed, then the wheels will remain turning just at the lower speed that we requested, matching our model. So a simpler solution to this was to just remove all of those lower wheel speeds, because the robot inconsistently moves at those anyways. Remember, this is open loop. And this was the less than ideal result. So this is, the robots are only allowed to move either full speed forwards, full speed backwards, or 0 for the forward speed. And for our turning rate, we allowed left, full speed, or right, or 0. And the results are what you saw here. We still don't quite get this sim-to-real transfer. But we had one more trick up our sleeve. Here we saw that the robots seem to turn actually faster in when they're not going forwards, when they're turning on a dime. And this was somewhat unexpected. Our linear mapping did not account for this. So a simple trick was simply to prevent them from moving with zero on either forward speed or turning rate. So they're always moving either forwards or backwards and always turning. And at long last, when we implement this, this is the result. The robots finally perform this milling behavior that we want. And over time, they will eventually close this gap. I will try and skip ahead a bit here. And we can see that this can continue on for quite a while. We eventually do just cut it off, but they don't break apart or anything. They just keep going. Here is the input and output plot for those robots. Whenever the background of a particular robot, each one of these is the input-output graph for a particular robot, and whenever the background is highlighted in green, during that time, the robot received a, it thinks it saw something, and whenever the background is a pure white, then it does not see anything. We can see that in the beginning couple seconds of the simulation, in the real world deployment, the velocity jitters back and forth a bit. They jitter around, moving back and forth for a little while. We don't know exactly why this happens. This is just one of the networks that was learned, but it actually did seem to spread the robots out if we look at, especially if we look out at these particular points in the output graph. And for the first little bit, the turning rate does seem to somewhat match up with our previous binary controller. When we see something, the robot will turn one way, and then when it doesn't see anything, it'll turn the other way. However, later on, it does seem to switch to this. It's a little bit hard to see, but for all of these portions of the graph where a robot sees something, it has this behavior where it jitters left and right instead of simply adhering to the binary controller where it will only purely turn left while it sees something or turn the other way. And this to us was a little bit interesting because we see somewhat of a bimodal thing going on inside the network. We think that in some way the network is changing to operate as a different sort of controller after a certain period of time, after around 8 seconds or so. And this is interesting because of the synaptic delay that I mentioned earlier. The maximum synaptic delay is 255 steps of a processor, which roughly works out, given our encoding and decoding setup and the outer simulator, the time step of the outer simulator, works out to around 3 or 4-ish seconds. But at around 8 seconds, that's way longer than than a single neuron to neuron delay can explain. So we think that some kind of other structure was learned inside the network, which makes this potentially very interesting. Another thing that I'll note is, although I don't have video for it, we set these robots up in the real world experiments in a couple of different initial configurations. We set these robots up facing each other, which is probably the worst possible starting configuration that you can have. And they collide with each other initially, but then they do still form this milling circle after a while. And that is also true for the binary controller, but it's true for the SNN. We tried a bunch of other starting configurations, and as long as we keep them relatively close to each other so that their sensing range is not exceeded, then they still form this milling circle in every starting configuration we tested in real life. So that is the work that we performed for this. And I would just like to note that milling is just one behavior. We have actually already tested another behavior with another metric, and we have found that we can get the robots to start in a certain region and then come together. And hopefully in the future we'll get some more useful behaviors. And that is all that I have. Thank you.